Hi grade 10s, this is Learn Extra Physical Sciences and my name is John. Today we're talking about a really interesting topic. It's about physical and chemical change. Now what's the difference? We know that there is change all around us. If we look in nature, we'll see change happening. There's the change from summer to autumn to winter to spring and back again. Now those are climatic changes, and together with those there are a number of processes that we can see happening around us that involve a change. So for example, you might be aware of the fact that in winter, when you breathe out, you will see there's this condensation that builds up in the air in front of you. When you go to a vehicle in winter, you'll see that there is a formation of frost or ice on the windscreens. How does this happen? What's happening? Have a same look on a winter's day at the field, and you'll notice that it's not white as it was in the morning. So there is change. We'd also recognize that if we leave, for example, a piece of metal out in the field, after a few weeks it will turn a reddish brown color, and we say it's rusted. We go into the household and we are cooking, and there are changes happening all the time around us. Now, when chemists explore these changes, they classify them into two types, and that's what we're going to have a look at. The difference between physical and chemical change, what are their properties, and how do we represent these changes? So that's what we're in for today, and it's a really important section because it builds on stuff that you're going to be required to know even in grade 12. So let's have a look at what today's topic is about, what we're going to cover. We're going to cover what is a physical change. So we're going to be looking at examples of physical change, describing them and representing them. We're going to look at chemical change, and there are a number of important chemical laws and principles that come into chemical change. And then we're going to be looking at ways of representing chemical change. Now, as I said, all of this is really important foundational stuff. So where do we begin? Well, let's start with some physical change. What do you think a physical change is? Well, I've already mentioned a number around us, and we are really well aware that matter exists in different states. So matter exists in 3 states. And physical changes are really, some physical changes are the conversions or the change of these states. So moving from a gas to a liquid to a solid, those are all phase changes or state changes. Notice that it's the same stuff. A gas has stayed a gas. The actual substance has stayed, has its characteristics, its identity. When it changes from a gas to a liquid, it's still the same stuff. It has the same chemical properties, the same, might not look the same, but it is the same. It's made up of the same molecules. No new substances are formed. Now, each of these stages you should remember are reversible. So we could also start with a solid and change to a liquid, and then from a liquid change to a gas, and even go from a solid straight to a gas, or from a gas straight back to a solid. We recognize that these changes in state don't produce new substances. I'd like to give you a couple of examples of some physical changes, and we'll start with this one over here that you'll have a look at. I have some ice cubes in the container, but as I've been waiting for us to start recording, at the bottom of the container we've already got some liquid. We'll have a look at this container in a little while, and we'll recognize that the solid has changed to a liquid. What about another one? Here's a one that you might see on a daily basis, depending on what products you use in your home, but I'd like to illustrate it for you. I've got an aerosol can here, and inside the can there is actually a liquid that's pressurized, and as I spray it out, you'll see that there are little droplets that spray out and they expand. Some of them are gases, and this fragrance now starts to spread and move from those droplets of liquid and spread through the room. And I'm beginning to experience those. So there's a compression that releases tiny little droplets of liquid. Those droplets of liquid then evaporate, they form gases, and they move through the room by the process of diffusion. This is a physical change. So no new substances have been formed. Here's another one that I think is quite interesting, and again, it might take a little while to get this one going. I've got some iodine crystals, and I'm just going to pour them out onto some filter paper here. Now, these crystals are solid at room temperature, but if we can get them a little bit hotter, then they will start to sublime. They'll change into a gas. I'm going to try and get that going in a little while. We'll leave it for the moment just at room temperature to see what happens, but I'd like to deal with a few more examples of some physical change. Often physical change happens in conjunction with a chemical change, and this is an example that I'm going to show you now that we're going to have a look at. If I take a candle and I light the candle, now, what we've got here is a reaction between the wick and oxygen, and it's producing for us some heat, a flame. But if you look carefully at the bottom where it's got nice and hot, what's happening is we're getting drips of candle wax. That dripping candle wax, you should recognize, is a process where we've got a solid changing to a liquid, and the liquid is then condensing and forming a solid. So if I show you the solid there, you'll see that it's actually formed a solid again. So there's a reversible process happening. Just by the way, because the wax was quite hot, I hope you can see as well that this iodine that was a solid little crystal has started to change color. And we've got some color change happening over there, indicating that we've got some gas being given off. And the color of the paper is even discoloring and forming a yellowish color. Okay. There is one other example of a physical change that I want to illustrate this morning, and that's what happens when we make a solution. Now, a solution is a special type of mixture. We are going to be studying solutions in a little bit more detail a little later on in another session, but here's an example. I've got a really nice crystal that I want to show you. It's got a bright green color, and you can see that there is a little bit of water in it at the moment. Some of it has started to dissolve. I'm going to add a little bit more water and just swirl it around. And what you'll notice is that that green color is changing to blue, and the crystal that was nice and big has almost all disappeared. So if I add a little bit more water and give it a shake and a stir, very soon there will not be any solid matter left inside this beaker. It will all be dissolved. It will have formed a solution. But now if we left that to stand in the sun for a while, the water would evaporate, and what would happen is that we would be left with crystals forming again. We can do this. If you take sugar, for example, put some sugar in water, go and leave it on the windowsill and see what happens after a few days. You'll notice that the water's evaporated and you're left with some solid sugar. New crystals of sugar. It's the same sugar, just been rearranged. Okay, so how can we explain what's happening? Now, I've shown you some examples that are that we would say are the macroscopic view of chemical change. Macroscopic because it's what we can see in the world around us. To explain these physical changes, we sometimes have to do two things. We have to say what's happening on a microscopic level, And secondly, how can we represent these changes in different ways? So let's go straight to that, and let's try and identify some of the characteristics of physical change. And we're going to be swapping between macroscopic and microscopic. So let's have a clear sense of what's going on. This, by the way, that we've said over here, the change between phase, which we can see and observe, this is a macroscopic observation, macroscopic view, if you like, of a physical change. What's actually happening, we're going to have to look at from a microscopic view to try and explain. And the first thing that you'll need to know, that if we look at a microscopic view, or submicroscopic view, the view of a particle, what do we know about particles of gases? Well, I'm not going to draw the detailed structure of the particles. I'm just going to draw some simple dots to represent molecules. Okay? But in a gas, what do we know about a certain number of molecules? Let's take 5 molecules. How will they be arranged? Will they be arranged close together, do you think, or far apart? Well, we know that in a gas, molecules are free to move. We understand this, that molecules are moving continually. And in a gas, at a certain temperature, substance will have enough energy for the molecules to move. There'll be large spaces. So if we had to draw the microscopic view of a gas, then what we would end up doing is we'd end up saying, well, there's a molecule there, and there's one there, and there's one there, and there's one there. And they're moving randomly. Because of diffusion, that one's moving that way, 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 within a container. And so they will bounce off the sides of the container. And let me just put the container into place. And you can see they're quite fairly far spread out. They spread out far apart from each other. There are weak forces between them, and they're quite happy. They're moving around. That's the view of a gas. So what happens when we take this gas and it changes to a solid or changes to a liquid? Well, what do you think? Let's have a look at the liquid. If we had those 5 substances, or those 5 molecules. Now remember, you could never really get 5. We put the same sort of container in place, same sort of size of container. What we'll notice now, for the gas view, for the liquid view at least, the gas view was far apart. What we'd notice for the liquid view is that the particles are generally much closer together. They're still randomly arranged. What we would see in this container, and I'm going to represent it over the top here, is that the liquid would occupy the bottom half of the container. It would be in a certain space, be confined somewhere like that. In this space, the particles are much closer together. So that would represent a liquid. Closer together, and we would call that the liquid. So what happens when we've got a solid? The arrangement of the particles is different. They are now arranged so that even if we had the container, same sized container, same sort of size, the particles now have their own shape. So they don't need the container to give them shape, but these 5 little particles would be packed together, and they would have their own shape, they would have their own volume, and we would say that this is a solid. Remember that when we change from a solid to a liquid, we say that process is the process of melting. And if we change from a liquid to a gas, there are 2 processes. The one is evaporation, which can happen at any temperature, but there is boiling. When the liquid can no longer exist, we say that process is boiling. The process of going back to a liquid is condensation. And the last one, going back to a solid, we can call it freezing. Or in some cases, like when those particles have evaporated out of a solution, we would say it's crystallization. It's the formation of crystals that have formed as a result of a physical change. Now, I hope that's got a clear explanation of physical change as it relates to the change of state. Let's have a look at the characteristics, and I've listed some characteristics. And the first one I've just explained to you, and I hope you've got that molecules change the way they are arranged. So molecules are arranged, the distance between the molecules can increase or decrease depending on what the change is. So if it's going from a solid to a liquid, it would increase. If it's going from a gas to a liquid, the distance would decrease. But now, what do we know about the number of particles? Now, you'll notice that I was very careful that in my diagrams, in representing them, I chose 5 little molecules or 5 particles, and I kept the number 5. They were always 5. So when we have a physical change, it's important that the number of particles stays the same. We're not introducing any new particles. Stuff doesn't just appear by magic. That doesn't happen in the real world. Might happen in the movies, but not here, not when we're studying physical sciences. So what we need to recognize, the number of molecules that were present in the gas phase would be the same as the number present in the liquid phase, same as in the solid. We're not losing anything. The number of particles stayed the same, and because the number of particles stayed the same, it stays constant, we say that the total mass of the substances remain the same. So that's kind of is obvious. If we've got the same number of molecules, they give us the mass. The mass of the gas is given by the molecules. We've only got 5 molecules. We've only got 5 molecules. There's no increase or change in mass. We'll come to a statement of that in a little while about the conservation of mass. Usually, for these physical changes, there are only small energy changes. Now, it does require energy to change something. So, for example, the iodine crystals that we were speaking about earlier, they're going to need a little bit of energy. If the room temperature is too low, they're going to need to heat up a little bit before they really get hot enough to change. The wax isn't going to melt from a candle, isn't going to melt at room temperature. It's going to need a spark of energy to get it going. But once that energy is there, it will allow the change to happen. So even at room temperature, we're getting changes in ice blocks, changing from ice as a solid to liquid water. The last point that I want to make here is that most physical changes are reversible. And we've tried to illustrate that by giving the names, but we've also seen it. When we melted the wax, we saw the solid changing to liquid, and then when it touched the piece of paper, filter paper changed back to being a solid. So we can change them one way or the other. We spoke about a solution, like the solution of copper chloride. If we take that solution, evaporate it, it will be reversible. We won't be able to capture all the water in that process, but we will maintain all the little crystals, all the little particles of copper chloride. Okay, so I think that's a useful summary of the characteristics of physical change. But as I mentioned just now, physical change doesn't always happen on its own. It's sometimes incorporated with chemical change. I'd like to show you an example of that, see if I can get it working. I want to have a look at some sulfur here, and here is some sulfur, and if I heat it up, now if I heat sulfur up, it will, using this, it will eventually melt. But if I do it directly onto the powder, we can see the melting taking place. And you can see the yellow substance is changing into a brownish liquid on the corner there. But if we leave it for a little bit longer, we might find that it actually catches on fire. And what's happening there is that sulfur is starting to react with the oxygen in the air and form a gas. called sulfur dioxide. We can't see it happening at the moment, but I hope you can see that that's what's happening. There is a melting process, and often when we burn sulfur, we are going to make a new product, sulfur dioxide. When we burnt the candle in oxygen, we lit it, and even if you take this little lighter and you hold it up, you are burning and you are changing, getting a new substance out of this reaction, which is a chemical reaction. We can't reverse it. There was a lighter fuel inside here, a liquid, and it's combined with the oxygen to form a new substance, and it's released some heat. So there are a whole lot of new processes happening. I just wanted to mention one thing about physical change that might just be quite obvious, is that there are some types of physical changes that are not phase changes. So for example, I could take a crystal and crush it. I could take a solid and grind it into powder. I've still got the same stuff. That's not a phase change. It's still a solid, but it is a physical change. You could take some chocolate and you could break it into pieces. That's a physical change. You've changed the shape of the original stuff. Substance that you were given, but you've changed it just by tearing and breaking it and putting it into smaller pieces. Those are physical changes. No new substance has happened. Even if you were to heat the chocolates and it melted, it would still be chocolate. But now if we had to do a chemical reaction, we are always going to get a new substance. I'd like to show you some examples of some chemical change. So let's just clear away some of the physical changes, and let's get on to some chemical change. So I'm just going to move those away and move that away as well. And I'm bringing this little beaker into view here. Hope you can see that beaker. Now, this looks like just a container with some water in it. What it is it's got certain substance in there with a color indicator. What I'm going to do is I'm going to add to this another liquid. And I just want to get the liquid out. And I want you to watch what happens. So if I put a few drops of this second liquid, hopefully, there we go. We're starting to see that there is a change in color. And now it's really got very different. I just want to give it a stir. And it's changed. Remember, this was red, and now it's a dark purpley blue color because there's been a chemical reaction. Now, that's one type of chemical reaction. It happens to be an acid-base chemical reaction. The red color was from universal indicator. The original substance was acidic, and I've added a base to it. Happened to be a liquid, and what's changed is it has changed the color of the liquid because the indicator changed color. We're not going into the detail of that particular reaction, but just to say that this is not a new substance is formed. It's not reversible. Let's have a look at another one. We've illustrated the burning one, and recognize that you can't put the lighter fuel back, or you can't put the wax that has burnt off back into the candle. The dripping wax you can recover, but the burnt wax that's gone into making the flame, that's not going to be recoverable at all. It's formed a new product, new substances. Let's have a look at another one, which I really like. And this one is quite spectacular, I think. So I'm going to take a common substance that you should be used to seeing, just some sugar, and I'm going to use some acid, sulfuric acid. This is not something that you need to be trying at home. It's very dangerous, but it's quite spectacular. I'm going to take some concentrated sulfuric acid and add it to sugar, and let's see what happens. Now, at the moment, the sugar is just changing its color, and you'll see the liquid is seeping down into the sugar, and it's changing from white to light brown. It's getting darker, darker brown. But in a little while, we'll get a reaction. The container is starting to get hot. We'll leave it for a few seconds and just watch what happened. Okay, watch carefully what's happening now. There is lots of heat being generated. Steam is being released, as well as some other gases that are really smelly and not very nice. And the sugar is changing into a black mass that is spiraling up and being pushed up as the heat expands and the gases are released from this sugar. And you can see a growing column of black emerging. And I don't know if we're going to get the volcano all the way up, but it's almost there. Let's see if we can get there. And it's just peeked over the top of the container, a black solid. Would you believe that this was once sugar? I don't think you would. That's clearly a new substance has been formed there. A chemical reaction has taken place. Now, we want to just make sure we've got all the characteristics of a chemical reaction. So let's go and have a look at those and compare them to the characteristics of a physical reaction. Right, what you've got here, the first point of a chemical change is that the molecules change form to form different molecules. So we start with a certain number of molecules, and they change not just their arrangement, but they change themselves. I think it's important that you understand this idea very carefully. So I want to just make a note of it. What we're going to say is that at the start, we have molecules that are known as reactants. Those are present at the start. So in the one case of that sugar experiment that we've just seen, your reactants would have been your sugar and your sulfuric acid molecules. What you need to recognize is we could draw those in different ways and represent them in different ways. But at the end, what are we left with? Well, in the simplest form, what we would say is we have a product, something that is different. So we don't have reactants anymore, but we have products. And the products is what's formed or present at the end. In our particular example, the simplest way of representing that, although there are a number of reactions taking place, would be say, yeah, we could see that there was some carbon and there was lots of steam, so that was water. So the sulfuric acid had a role to play, but it didn't really formed a special role. This sulfuric acid here, we say, is a catalyst. And it didn't really change itself. There was some sulfuric acid left over, although the reaction itself is more complex than I've illustrated here. So sugar has changed from carbon to water is the simplest way of describing that reaction, but in reality we could say there are a number of other things taking place. But what I hope you can see is that we've got different stuff. Not just the same molecules or the same group of atoms. The atoms themselves haven't just moved apart. They have changed partners. They have regrouped. They have broken bonds, and they've formed new bonds. And that's really important for us to understand. Now, the important thing here is that we recognize that in any chemical reaction, not like the physical change that we spoke about, is that the number of molecules we're dealing with a particular number of molecules at the start, that usually changes because we're making new things. We're taking a little, think about it like building Lego blocks. And you started with a certain number of Lego blocks to form a molecule. And with physical change, all that's happened is that those Lego blocks, components, those 5 little components, have either moved further away from each other or closer together, or even if they were close together, we've separated 3 in one group and 2 in the other. It's still the same number of molecules. Here, what we're saying, let's take the Lego blocks and break them apart into smaller bits. So there might have been inside the molecule number of different bits. We've changed the way that they've reacted, put all the blues together, all the reds together, and we've changed the order. So we've got a different number of molecules. Let me do an example to show you what's happening there. A particular example that we can have a look at. Very simple reaction that we haven't done, but one that will work just as easily. If we say, let's take some carbon. So we're going to take some carbon. Sorry, spelling is incorrect there. Carbon and oxygen. And when we burn those two together, similar to what you've seen with the candle and with the lighter fuel, but this is more like getting a briquette that you're using for your braai. And we're going to take pure carbon and we're going to burn it in oxygen. Then you're going to get carbon dioxide. Now, let's pretend that we've got 2 of those, and we've got 2 of those. So total of 2 atoms of carbon, 2 molecules of oxygen. And what we're going to get here is carbon is going to link up with an oxygen, and I'm just drawing that representation like that, and we're going to get another one. So 2 carbons are still 2 carbons. We had 2 oxygen molecules. Now remember, an oxygen molecule is diatomic, so it's O2. And what we're seeing here is, to start with, we had 4 particles or 4 molecules, if you'd like to call them that. And at the end, what have we got? We've only got 2 molecules. That's on a microscopic level. What I want you to understand here is that we can only count the number of molecules and make sure that we've got the number of molecules when we start to draw diagrams and represent what's happening at the microscopic level. Mass-wise, has there been a change in mass? Well, what do you think? Did we have any new substances? Did we knew the mass of the reactants? What do we say about the products? Well, just the reactants have interchanged. They've changed partners. So the mass stays the same, and that's exactly what we've said over here as our third point. The total mass of the substances present remains the same. There are usually large energy changes. So different between physical and chemical. Chemical, large energy change. Now, when we did the reaction, even pouring the sulfuric acid into the sugar, that container got really hot. So hot that we generated steam. And it was too hot to hold the glass. It really released lots and lots of heat. So you need to recognize that there are large changes. Even when we light the lighter, we're getting heat being released. There's a chemical change. And the indication of the heat being released is the flame. The gases, oxygen and the lighter fuel, form gas, and there's a little spark that gets the reaction going, and it then carries on producing the yellow flame, a release of light and of heat. So we can make sure of that. The last point here is that most chemical changes are not reversible. Now remember, we saw when we did physical changes, we had the wax burning and melting, and it changed from solid to liquid, and then it formed a solid again. Now that is a reversible process. discussed reversible processes. When we come to chemical change, we can't take that black carbon and the water that's been released into the atmosphere, and even if we could collect all of them and shove them together and get white sugar. No, can't do it. It's not reversible. Now, there are some chemical reactions that are reversible. Mustn't exclude that possibility, but most chemical reactions are not reversible. So your nail or your piece of iron wire that's left out in the field, it's going to rust, falls apart. Iron changes to iron oxide. Very difficult to get iron oxide back into metal. So we can try in different ways, but we're not going to be very successful in most cases. In most cases, it requires more energy than it's worth to reverse most chemical reactions. If we have to take something else, like the reaction of a metal and an acid, we're going to produce a salt and hydrogen gas, and again, not easy to recover the metal from the salt. It's possible in some cases, but not easy. So I need you to understand that where most physical changes are reversible, chemical changes generally are not reversible. Okay, I think we've got a good comparison, and you've seen both the physical changes on a macroscopic level, and we've compared the differences between physical and chemical. We're going to go to a short break, and after that break we've got a few more important features or laws that we're going to discuss, and then we'll get into some questions on physical and chemical change. So don't go away, take a break, and we'll see you after the break. Metal and an acid, we're going to produce a salt and hydrogen gas, and again, not easy to recover the metal from the salt. It's possible in some cases, but not easy. So I need you to understand that where most physical changes are reversible, chemical changes generally are not reversible. Okay, I think we've got a good comparison, and you've seen both the physical changes on a macroscopic level, and we've compared the differences between physical and chemical. We're going to go to a short break, and after that break we've got a few more important features or laws that we're going to discuss, and then we'll get into some questions on physical and chemical change. So don't go away, take a break, and we'll see you after the break. Hi grade 10s, welcome back from the break. Now we've been talking about physical and chemical change, and there's one last thing. When we spoke about physical change, I said we'll wait a little while to see some physical change taking place. Remember, we had two examples, and I don't want you to forget these examples. We're going to compare them to chemical changes that we've seen earlier as well. So let's just go and have a look here. And the first one, we had some ice in the beaker. And what you'll notice is that although we still have some blocks of ice, and I can take them out, what you'll notice is at the bottom of the beaker, there is now some liquid water. So that's clearly a physical change. It's the same stuff. The mass hasn't changed, it has remained the same. Whereas if we look at the iodine, this filter paper has changed, and it is becoming a darker and darker brown yellow, and some of the iodine little crystals have started to evaporate. Well, they don't evaporate, they're changing into a gas. When we change from a solid to a gas, we call that sublimation. So in both of those examples of physical change, what we need to recognize is that no new substances have formed. We also recognize that the mass of the particles hasn't changed. I understand the iodine might have disappeared into the air as it's sublimed, but what we need to recognize is we could capture all of those iodines, get them to crystallize again, and we'd have the same reversible process. But the important principle here is, both for physical and chemical change, mass doesn't change. That's what they have in common. And we have a principle or a law that we state. When we say this, we say it's the law of conservation of mass. Now, conservation doesn't mean looking after wildlife in this case. It means it's conserved. It means it stays the same. It's a strange physics term that we use in chemistry as well. We're going to look at a number of laws of conservation. It means that there is no change. So there's no change to the mass. The way we state it is as follows. We say that the total mass of substances taking part in either chemical or physical reactions is conserved during the reaction. Matter changed form, but can't be created or destroyed by physical or chemical changes. So that's really important. We can't suddenly be making new elements or somehow adding to the container. Things don't come from nothing, and we can't take matter and destroy it. It will always form either a new substance or it will form the same substance that it was originally. Now, that's the law of conservation of mass. It doesn't matter what type of chemical reaction, whether it's one where we're putting things together. When we're putting substances together, we say that would be a synthesis reaction. So I just want to mention two types of reactions here. Synthesis, where we take reactant A plus reactant B, and we get reactant or product AB. That's a building up. It's making new substance. There's the new substance. Now, the reverse of that process is decomposition. So we could start with one substance as the reactant. So we'd start with, let's say, CD, and we break it apart by heating or any other processes, usually heating, and we make C plus D. That's decomposition. So what do you need to recognize? It doesn't matter where you are, what type of reaction. Generally, those two reactions, synthesis and decomposition, are very general of all types of reactions. But in both cases, mass is always conserved. It doesn't matter. You can't destroy matter. It's only in nuclear reactions. But for physical and chemical change, not possible. Okay, now there's something else that I want you to know about the products formed when we're doing chemical reactions. And this is a law that some people don't really understand too well, but I want to try and explain it to you. It's called the law of constant composition or proportion. The law of constant composition or law of constant proportion. It says any given chemical compound, the elements always combined in the same proportion with each other. So let's take an example. If I take hydrogen and I take oxygen and I combine the two of them, I can make water. Now in water, you know that the chemical formula for water is H2O. Now, it will always be H2O. Whenever you combine hydrogen and oxygen and you're wanting to make water and the conditions are right to make water, then what this law is saying, in the compound, water, it will always be 2 parts of hydrogen to 1 component of oxygen. The ratio of 2:1. There is a second part to this law that's called the law of multiple proportion, which says that, yes, we're making water, it's 2:1, but that doesn't mean that you can't take hydrogen and oxygen and make another substance from it. It will have different chemical properties. So if we take a look at something like hydrogen peroxide. Now, the formula for hydrogen peroxide is H2O2. Now, normally we wouldn't write that like that because we would say we want to have a simplest whole ratio, but this is the molecular formula and it's the one that's agreed on. What I want you to see here, the ratio is 2 hydrogens to 2 oxygens, which is a ratio of 1:1. Equal ratio, different to water. So there are 2 possibilities. Water will always be 2:1. Hydrogen peroxide will always be 1:1. 2 hydrogens to 2 oxygens. Different stuff. Okay. Now, the last little bit of theory that I want to deal with in dealing with chemical change, and it's an interesting principle, we're going to do some problems related to it just now, is a law about gases. and many reactions take place as gases. We need to understand something about gases. They are taking the volume of the container. They are determined by the pressure and the temperature. So the amount of stuff when we're dealing with gases is determined by those three things: temperature, pressure, and volume. If we have the same volume of gas, different gases, then this very famous physicist, number of years ago, Guy Lussac, he said if you've got the same volumes, then you're going to have the same number of particles. So let me show you what Guy Lussac's law says. It says in a chemical reaction between gases, so we are only dealing with gases, the relative volumes of the gases in the reaction present are on the ratio of whole numbers, if all gases are kept at the same temperature and pressure. So let me try and explain this to you. If I have a container and I have a second container, same pressure, same volume, same temperature. This one contains nitrogen. This one contains hydrogen. Then what Guy Lussac and another man called Avogadro hypothesized was that the number of particles inside here would be the same as the number of particles inside there, even though the mass of this one is not equal to the mass of that one, because the hydrogen is smaller molecules, nitrogen bigger molecules. Masses aren't equal, but the number of particles is. Number equals number. Now, how we apply that to a chemical reaction is if we say take a reaction of nitrogen and hydrogen to make a gas called ammonia, then what Guy Lussac's law is saying, if we know have a ratio of particles reacting, the volumes, if we have two volumes in a set ratio, we have the ratio according to the way the reaction goes, then we've got the right number of particles. We can use the ratios to determine the number of particles. Now, we're going to illustrate that very carefully in an example, but I think it's an important law that we will come across and you'll need to learn. So let's get straight into some examples now. We're going to do a couple to differentiate between physical and chemical change. Let's see how you manage on these ones. Here's first question. It says, for each of the following, say whether a chemical reaction has taken place, or a physical change, physical or chemical change. Well, the first one is easy. We've seen it already. And I just want to remind you that melting candle wax, that is going to change from a solid to a liquid. And we have seen that you can change from the liquid back to the solid, so it's reversible. We also would recognize that the number of particles are conserved, so this is clearly a change in phase. It is a physical change. Right, ready for the next one? Let's have a look. This example says we're going to mix some substances together. We're going to take some sodium chloride and we're going to take some silver nitrate and we're going to put these two beakers together and we're going to make some sodium nitrate and some silver chloride. Can you see what's happened? Well, I don't think it takes too much to see that the nitrate has changed partner and the chloride has changed partner. So where sodium had chloride as a partner, it's got nitrate as a partner. So what have we done? We've made new stuff. As soon as you see that we've made new stuff, what can we conclude? This is a chemical change. what you will notice if you do this on a macroscopic level is you will get in the solution a lovely precipitate forming, white precipitate. That means at the bottom of the beaker you'll get a white substance forming that you will clearly see. Now, what about this one? We've got hydrochloric acid, and we've got magnesium ribbon. And it tells us that what we're going to form is magnesium chloride. The name is given as well as the formula. So what we're recognizing here is hydrochloric acid was given as a formula HCl, and magnesium is given as Mg, and what we're forming is MgCl2. So what do we know about that? That's a new substance. So this must be a chemical change. Now, that isn't a complete representation of the whole reaction, but we have identified that it is a chemical change. So we wouldn't write that down like that in an exam if we were asked to describe it. We're coming on to representing chemical changes in a minute. Now, here's an interesting one. Dissolving sugar in water. Well, we had an example of that sort of process. We took not sugar, but we took copper chloride, put it into water, and we dissolved it. We also said that you could do it with sugar. Molecules of sugar would move further apart from each other. So if we had to represent this on a macroscopic level, we would say, microscopic level at least, we'd have sugar as a solid, and when it got into solution, we'd have something like that. They spread out, and in between these, they'd be surrounded by some water molecules. So they're the water molecules sitting around the sugar, and they're in solution. So have we made any new stuff? Well, no. They're still the same. The sugar hasn't changed. They've just moved further apart from each other. And to be absolutely accurate, I should make sure that the number's the same. I started with 6 and I've got 6. This was a solid. This is in solution. If I heat, take away the water, I can easily get back to that. So this is a physical change. Okay. Now, we're going to be dealing with solutions in a later session, but the chemistry here is quite interesting. And you need to understand that when we move things apart from each other, physical change. Okay, no new substances have been formed. Right, last one. We've got a piece of magnesium ribbon, and we take that piece of ribbon and we tear it in half. What have we done? Have we lost any substance? No, we've got the same number of molecules. Can we reverse it? No, not very easily in this case. Suppose we could melt it in an inert environment and reform it. Might work. But the same number of particles are there. No new substances are formed. Clearly, this is a physical change. Right, let's move on. I think we've got another question coming up here, and the chemical equations that are written below. Now, this is an interesting thing. What we're going to say is that in some cases we represent chemical change by an equation. And you've done some equations before. We'll get to those. For each equation, draw a diagram. So we have to draw a diagram showing the reactant molecules and a second diagram showing the products, and then use the diagram to decide what type of change has taken place. So I just want to go to this particular diagram, this particular equation now. We're dealing with substance that has got carbon and hydrogen. You don't have to know the name of this, but I will write down the name for you. And then I want to just add something to our diagram here. You might not be aware of what that represents. The L and the G represent the phase. We call these phase labels or state labels. They are phase indicators. And the phase here is the gas phase. This is the liquid phase. Now, you could also have one in brackets, which is S, indicating solid. And the last one, which is quite interesting, is AQ, and that represents a solution of water. So it's formed a solution where the solvent is water, so the stuff doing the dissolver, solution of stuff in water. So it's of a solid in water. That's what aqueous, aqua meaning water. So we haven't got that now, but I just wanted to make that note on phase indicators. So what have we got here? Something, don't even have to know its name, is changing from a liquid to a gas. Well, what do you think that is? Well, that process from liquid to gas, we know is could be boiling, or it could be evaporation. And that is clearly a physical change. So we can identify physical change. Now, we've got to draw pictures. So the reactant, I'm not going to draw all the atoms in, and they're the products. So what are we going to say? We have started with a liquid, and we're going to a gas. I'm just going to choose a symbol to represent my molecule. So I'm going to represent my molecule with those little yellow ovals. I'm going to say as starting as a liquid, these are quite close together, but when they become a gas, so this is liquid, and this is a gas, what can we say? They're going to be further apart from each other. But we need to remember that they're the same number. They haven't changed. They haven't changed size. They haven't changed any. All they've done is they've moved apart. So from there to there, we've gone from liquid to gas, and it represents the change that has happened, a physical change. Let's go to the next one. And here we've got another set of gases. But notice what we've got here. We've got nitrogen. There's nitrogen as a gas, hydrogen as a gas, and ammonia as a gas. Now, recognize something here. From this reaction, we recognize that we've got one volume, we've got 3 volumes, and we've got 2 volumes. That number in front tells us the number of volumes or the number of molecules. What we're saying is that we've got 3 times the number, so it's 3 times the number of molecules here. We've got 2 molecules here, 2 times the number of molecules, and we would only have a certain 1 times the number of molecules. That's Gay-Lussac's law. We're saying the number of the volumes are going to depend on the number. From the number of atoms or the number of molecules, you can determine the volumes. So in one volume, you would have the same number. So this 3 is saying 3 times the number of molecules. So we need to note that, and we need to draw the diagram. So let's draw the diagram for the reactants first of all. So we're going to say reactant. And we're going to, first of all, deal with nitrogen. So nitrogen and hydrogen are the reactants. Remember, in this reaction, we are going to need to make sure that we obey the laws, all the laws that we've spoken about, constant composition, as well as the conservation of mass. So when we draw diagrams for this sort of process, we need to make sure that we've got it right. So I'm going to represent the nitrogen molecule by 2 little green atoms, 1 molecule. The hydrogen, I'm going to use white, and I'm going to draw them smaller, 2 of those. Now, I don't just want to have the ratio of 1 to 1. This tells me I've got to have 3 hydrogens. So I'm going to put in another 2 like that. Right? Now, what's this going to form? Well, let's see if we can get it to do it. Have a look at the product. The product was NH3. So what it's telling us from the chemical reaction or the chemical equation that we need 2 of those. So let's take 1 nitrogen, put it down, and for every 1 nitrogen we need 3 hydrogens. So I'm going to take this hydrogen here, let's just take that one. And I'm now going to take 3 hydrogens. I'm going to take those 3 there, and I'm going to put them on. So 1, 2, 3. What have I got left over? Let me do my accounting correctly. I've got 1 more nitrogen. There it is. I've taken it. And I've got 3 hydrogens. Hope you can see now that the number of atoms hasn't changed. The number of atoms hasn't changed. I had 2 atoms here, I had 6 atoms here. I've still got 2 nitrogen atoms, I've still got 6 hydrogen atoms. The number of molecules, I started with 1 molecule of this, I started with 3 molecules, and I've ended up with 2 molecules. Now please note, the mass will be the same. It makes sense. The mass of the reactants will be equal to the mass of the product. The conservation of mass has to be illustrated. So you could have a different number of nitrogen molecules to start with, but you need to make sure it's in those fixed ratios. The numbers have to correspond, and they have to bond according to the law of constant composition as well. Ammonia will always be 1 nitrogen and 3 hydrogens, and that's why we've got to keep these balanced things in balance. So what's happened? Have we made new stuff? Yes, of course we have. So this must be a chemical change. Right, almost the last one. And we've got here a reaction where we've started with a particular stuff, a substance, a solid, and we're producing 1 solid and 1 gas. Notice that this is a decomposition reaction. And as soon as you recognize new substance, you can say chemical change. How are we going to draw it? Well, let's just put it down and see how we go. We've got 1 calcium, we've got 1 carbon, and we've got 3 oxygens. I'm going to use the white ones to represent the oxygen. Do it like that. And they fall apart to simply form 1 calcium and 1 oxygen, and then 1 carbon and 2 oxygens. Now, when you're drawing diagrams like this, it doesn't really matter the size doesn't matter. We're just trying to show that there's a conservation of mass, and we're also showing that there's a conservation of the number of atoms. We're showing that there's a new substance formed. There are new substances formed, and so we can therefore indicate that this is a chemical change. I think we've got 1 more over here. And this one is really quite interesting because it deals with the process that we've observed. Liquid water changing to, or we observe almost every day. We haven't seen it today in the studio, but liquid water changing to gas, to water gas in the gas form. When we watch a kettle boiling, you will see steam. Steam isn't liquid gas. Or water in the gas form. What's happened with that steam? It's already started to cool down, and you see the droplets are attaching to little particles in the air. What's interesting about this one is we've got oxygen there, and let's put in 2 hydrogens. And if we have oxygen still over here and 2 hydrogens, I hope you can get the picture that the molecules haven't changed. That's what the equation is telling us. Obviously, over here we would say, well, we've got more than one, and they're closely packed together. If we wanted to illustrate what this is saying, that this is a liquid, well, these ones are close together. But if we were illustrating the gas, we would say, well, look, that one is far away. That would represent a gas. Still, what sort of change? A physical change. Right, and this is the last one. Now, this is quite interesting, the way it's been written. But let's have a look at it. What are we starting with? We're told that we've got a solution. We're told that we've got a solution of sodium ions plus charge, chloride ions, and we're making sodium solid and water. That's the product. The aqueous says that they were in solution. So let's use that as the positive, and let's use a different color as the negative. We're going to just put a little negative there. We're going to put a little positive over here. And what we're recognizing is that they have joined together to form a different structure. They formed a structure that one could almost think is a new substance. Whereas the water wasn't present here, it was trapped around there. If we had to actually illustrate it, we would have to say, well, there's a water molecule, and the water molecule has been formed over here as well. So did the water change? No, the water didn't change. And this is where there is some debate. Science isn't always clear-cut. We recognize, we can see the picture, water and water, there's no change. So let's just analyze this for a second. We recognize there's been no change there. The position of the water has been different. This has changed from being surrounding these ions. This has gone into the gas phase here. It's evaporated. So there has been a change that we might be inclined to say the water has undergone a physical change. The water. But what's happened between the sodium ions, these are ions, and this is an ion? Well, they've got closer together. Now, they've got closer together and they've formed up into a new structure. There are some people that will say, because they've formed a new structure, and because they're not exactly the same as they were before, this is a chemical change. But the community, the science community, is actually divided. The more common interpretation is the ions were separated, and they've actually just got a little bit closer together, and so it is a physical change. I would suggest that if you're given something like this in a test or an exam, we'd recognize that this is an unusual situation, but most people will describe this as a physical change. So I'm going to describe it as a physical change. Because particles haven't really changed. These are still positive. That's still a negative. They're just closer together. They've attracted together. They're bonded by ionic bonds. Now, please don't get confused. You don't get a salt crystal with just one positive and one negative. There are thousands of them. I'm just representing these diagrams because I haven't got time to draw thousands and thousands of them. Okay, now I think at this point we need to go to a short break, and directly after the break we're getting into some more detail about how to more accurately represent chemical change. So I'll see you in a minute. Welcome back, guys. Now, we've been representing and discussing physical and chemical change. And the important part of chemistry here is how do we represent these changes? These changes, most often, we can draw diagrams. Those aren't very practical. We can write word equations. Those also don't tell us the full picture. What we need to be able to do is represent what's happening using symbols. And so there are a number of steps that we can do using symbols to represent chemical change. We call this writing a chemical equation. So writing a balanced chemical equation. Now, I can't stress how important this is. Learners need to recognize that in grade 12, if you don't write a balanced chemical equation, you're going to get way wrong in your calculations. It's really important, grade 10s, that you get 2 things right this year, and it's all that you learn in chemistry. It will be sufficient. Writing formulae and balancing chemical equations. Now, there are a number of steps that we can go through, and these are in your notes. I'll just refer to them very briefly, and then we'll practice them as we do some equations. So let's go to the steps. The first step that you're going to do is you're going to identify what your reactants and products are. The things that you start with are your reactants. The things that you end with are your products. This is present at the end. Then you need to write the chemical formula. We're going to practice some chemical formula just now, but it's important that you've got that right. You can't change the chemical formula. We write the equation by putting the reactants on the left side of the arrow and the products on the right. Straightforward up until this point. Then we're going to count the number of atoms of the reactants and count the number of the products. We want to make sure that mass is conserved. Conservation of mass. Mass must be conserved, the number of atoms must be conserved. So if the equation is not balanced, we're going to change the coefficient. The coefficient is the number in front of the molecules until we get the balanced equation, and we'll check that the total of each is the same, and then once we've done that, we must put in the phase indicators if they've been given. Okay, so those 6 steps will make sure if you follow those, it's just a matter of practice. Counting and practice, and soon you'll be able to do it in your sleep. But the important thing is that you do them and that you practice them. Right, so where do we start? We're going to start by writing down some chemical formula, just to remind you of chemical formula. And I've chosen a couple here for you just to practice on. Magnesium hydroxide. So magnesium is in group 2. The symbol is Mg. Hydroxide is a polyatomic ion, OH. What you need to remember is that the polyatomic ion is negatively charged. Has a charge of -1. So magnesium will be +2, group 2 loses 2 electrons. This one is -1, so we put it in brackets and we put a 2 down there. So please remember that. Magnesium, 2+, hydroxide, -1. We're going to need 2 of those so that the charges become equal. When the charges are equal, we write them like that. Right, next one, calcium nitrate. Calcium also in group 2, nitrate, NO3, and it was minus. So calcium +2, nitrate, NO3 minus. Again here, you need to make sure what the polyatomic ion, the nitrate ion, learn it, make sure you've got it. It acts as a group, so we put brackets around it. And we're going to need 2 of them, so we're going to put a 2 over there. Right, next one. Ammonium phosphate. Now, here's one you have to learn. We dealt with an equation earlier that had ammonia in it, but ammonium is NH4 plus. So NH4 plus 1. Phosphate, PO4 minus 3. What does that mean? We're going to need to make sure that the positives and the negatives balance. So I'm going to need 3 positives, 3 ammoniums, and 1 phosphate. The ratio is 3:1. Law of constant proportion, constant composition, always the same. So when we write it, we're going to need 3 of the ammonium, in brackets 3 with 1 PO4. The ratio 3:1. Next one, iron 3 sulfite. Now sulfite, SO3, and it has a charge of 2 minus. iron 3 plus 3. How are we going to get those right? Now, it's not a case of multiplying 1 and getting to the common number. We're going to have to cross multiply. And that means you're going to multiply 3 by 2 and 2 by 3 to get the common number of 6. So we're going to have a positive 6, negative 6. So let's do that. You can do the crossover that way and recognize that's how it's going to be. I'll write it like this and then check it. 2 brackets, 3 of those. Let's check the charges. 2 times 3 is plus 6. And 3 times minus 2 is minus 6. So we know that we've got it right. Last one, different format for an equation. Sulphur trioxide. Now remember, symbols or formula of chemicals can be given in different notations. The tri there means 3. Di means 2. Tetra means 4. So we're dealing with sulphur trioxide. We're going to write it down as sulphur with 3 oxygens. And there it is. The alternative name for this particular substance is sulphur 6 oxide. And the reason for that is because of the valency of the sulfur in this particular compound. So it'd be a little unfair of us to see. Oxygen always has a valency of 2, so that's why we need 3 oxygens. 3 times 2 will give us 6. So that's the other way of making sure we've got it right. Okay, let's move on. These are the challenge questions now in terms of balancing equations. Right, here we go. We've got barium chloride reacts with sulfuric acid to produce barium sulfate and hydrochloric acid. So what we're going to do is write down the formula. First of all, barium chloride, BaCl. But barium is in group 2, so it's Cl2, plus sulfuric acid, H2SO4. Now, just to make some space, I'm going to write the products underneath. Please don't do that. You might write them all on the same line, but I'm doing it here so that you can see it. And we'll put the arrow over there. The arrow would normally all go on one line. So now we're going to balance the equation. Let's check the number of bariums that we've got. We've got 1 barium in the reactant, and we've got 1 barium in the product. We've got 2 chlorines over there. We've only got 1 chlorine over there. We've got 2 hydrogens over there, 1 hydrogen there. 1 sulfate group over there, 1 sulfate group. So to me, it looks like the problem areas are those 2. And I need to get 2 in both situations. The way I'm going to do it is I'm going to simply put a 2 in front of the hydrogen. Now I've got 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, 1 barium, 1 barium, 1 sulfate, 1 sulfate. The equation is balanced. Hope you've got that. Move on. Right, let's get this equation written down first of all. Remember, the first step is to write down the correct formula. They've been very helpful by giving us the formula for ethane, which is C2H6, which is that one, plus oxygen, O2, reacts to form carbon dioxide, and then we produce steam, which is water. Right. Write down the correct number of each things on each side. 2 carbons, 6 hydrogens, and 2 oxygens. We've got that. On the product side, 1 carbon, oxygens, 2 over here and 1 over there, 3 oxygens. Hydrogens, only 2. Now, to get this one balanced is not straightforward. So we're going to need to juggle some things around. I like to get even numbers. If there are even numbers of things on either side, I'd try and keep that in my head. But you also need to make sure we balance things. You can't just balance one thing at a time, because then you're going to go backwards and forwards and find it quite difficult. So I'm going to start over here and recognize I want to get the hydrogens and oxygens sorted out. 6 hydrogens. Looks to me simple. I could put a 3 over there in front of the hydrogen of the water. That would give me 6 hydrogens. But at the same time, I want to get the oxygens to being even. So I've got an even there and an odd there. I want to get an even number in front there. So if I make it a multiple of 6, then that will be cool. So I'm going to put 6 over there. Then 6 times 2 is 12. So I've now got 12 hydrogens, which means that I can easily change the 12 and I'll get that in. What about the number of oxygens now? Instead of having 3, I've got 6 plus 2, which is 8. Okay? So I've got 8 on that side. Now, on this side, I'm wanting to make sure that I'm going to get 12 hydrogens. So I put a 2 in front there, and that will give me my 12 hydrogens. But by doing that, it changes the carbons to 4. So 4 carbons, I need to get 4 carbons on this side. So I'll now put a 2, I put not a 2, I want to put a 4 in front of the carbon dioxide. So it was carbon dioxide, and I'm going to put a 4 in front of that. So now I hope you can see, where are we? We've got 4 carbons over there. Looking good at this stage. Let's check our hydrogens. Hydrogens, we've got 12 hydrogens, and we've got 12 hydrogens. So those are fine. So all that's left to balance is the number of oxygens. By putting the 4 oxygens there, I have changed the number of oxygens. So I need to recount my oxygens. How many oxygens have I got? 4 times 2. 4 times 2 is 8, plus 6. 8 and 6 gives me 14. So I've got 14, and on this side I've only got 2. How am I going to get 2? Well, it's diatomic. I can easily get 2 by putting a 7 there. Right, now, that was quite a mouthful, but I suggest you practice and practice some more, making sure that you balance equations correctly. It's very important. Well, I hope you've enjoyed this session dealing with physical and chemical change and representing those. We'll see you again soon. Bye from me.